Welcome to this new demonstration of the Data Fusion Labeler dFL, where we'll walk through the process of harmonizing and labeling simple multi-year weather data. In this example, we'll be working with approximately 10 years of meteorological records based on latitude and longitude for Boston, Massachusetts. Each yearly record contains 3 signals: precipitation, temperature, and pressure. The data are fetched using the built-in weather data fetcher utility located in the project's data/folder that utilizes the Python MediaStat library available via pip on mediastat.net. This data fetcher can easily be customized to query other geographic coordinates by simply updating the latitude and longitude parameters. Let's begin by opening the dFL workspace and loading our data source. In the interface, navigate to Settings, Open File. Select the local file weather_data_provider.py. This file holds about 10 records, 1 per year, and click Save Settings. The dFL automatically infers signal types and applies preliminary harmonization filters: precipitation, millimeters per day, temperature, degrees Celsius, and pressure, hectopascals. Once loaded, we can visualize the dataset across years. We can also normalize the data so that the multimodal dynamics are revealed. The timeline browser shows each record as a distinct entry, and the Data Explorer confirms that all 3 signals are properly aligned by timestamp. Now let's use prompt-based customization to add an interactive visualization. In the prompt console of your IDE, make sure to add the file context.md to your prompt. Then type, create an interactive precipitation plot per record that highlights time periods exceeding a user-defined threshold. Add the capability to the @weather_dataprovider.py and/or @weather_utilities.py. dFL interprets this as a graph customization request and generates a live threshold-controlled visualization component. After the update is finished in your IDE, which may take several minutes and require some interactive responses, you can open the modified data provider file in dFL or force reload under view in the main. A new graph type should appear under Graphs called Precipitation Threshold. Under this graph type, you can select the threshold value, e.g. 20 millimeters, and the signal to plot. The plot shows areas that rise above the threshold by marking them, and the plot should be interactive with your mouse. As we move the slider, dFL dynamically highlights segments of each year where precipitation exceeds that threshold. Next, we'll add a simple but powerful automation, a custom auto-labeler that generates persistent labels whenever precipitation surpasses a chosen threshold. In the prompt interface, type, add a custom auto-labeler called Precipitation Threshold to the attached data provider and utilize that labels all intervals in which precipitation exceeds a user-specified threshold. The IDE responds by creating a new provider subclass within the project's pipeline. Again, this may take several minutes. Again, after the update is finished in your IDE, which may take several minutes and require interactive responses, you can open the modified data provider file in dFL or force reload under view in the main. The new auto-labeler listens to the precipitation signal during data fusion and automatically appends new label objects to the dataset. This auto-labeling can be performed across all records or years in one click. The resulting labels are persistent, stored directly in the dataset's harmonized metadata layer, and can be filtered, merged, or exported for downstream modeling. You can view your current labels from the Current Labels button in the main control panel, which shows the labels for the selected record. To export the labels, navigate back to Current Labels, then simply click Download Labels from All Records. This will bring up a Save to Directory prompt, where an output CSV file will be saved. These labels can now be used to train a precipitation predictor, where the goal is to infer future precipitation from historical temperature and pressure trends. Because every transformation in dFL is recorded in a version-controlled data lineage graph, this model remains fully reproducible and interpretable. In summary, this demonstration showed how dFL enables users to 1. Load and harmonize multi-year, multi-signal weather data. 2. Create interactive, threshold-based visualizations through natural language prompts. And finally, 3. Integrate a custom auto-labeling routine to generate ML-ready datasets. Thank you for watching, and to learn more, visit the dFL website, dfl.sophelio.io.